Okay, we're on the air. So what? So
So it's quantum.
to summarize in homework one, so that the radius at which you could emit photons in black body spectrum, if it's really a black body spectrum, would have to be from a very compact region, maybe 10 to the ninth centimeters, or a few times that. Whereas uh, it should only become opaque. It should only become transparent, even if you manage to get it to a gamma of 100, which is another big question. But even then, it would only become transparent at 10 to the 13th centimeters. And
What if it?
why do we pick gamma of 100? It's because if it became transparent at 10 to the 13th centimeters, uh, you might think that 10 to the 13th centimeters is 300 light seconds, right? And if you multiply by 1 over beta, 1 over 1 minus beta, which is the time compression, uh, then if it's really a thin shell that's emitting, um, maybe uh, the time over which you see it is much less, because the observed time.
By the way, what if you see thermal radiation coming from, let's say, 10 × 7 to the 9, and the time when thermal radiation was emitted, the envelope was at 10 × 12, so they cannot really the envelope cannot obscure, so the photon moving at the speed of light, so they cannot catch up with the envelope.
That's a good idea. I just wrote a paper. Uh, well, um, no, the most recent paper, I suggested that they did catch up and scattered off at once, and it's okay. I suggested it doesn't even matter that it's opaque, as long as it's transparent on the inside, because if the photon hits the opaque shell and scatters backwards, if the opaque shell is moving at high gamma, then the transformation in the angle in the observer's frame is actually outward.
Yeah.
In other words, it's going outward, but it's going outward more slowly than the shell, and by the time it hits the shell again, a second time, the shell is already
But
transparent.
isn't there a problem energetic? That means because the number of photons that are emitted backward is much less compared to the photons that are emitted forward. So that means if we
Mm, no, let's say most of the action is on the back end. Let's say all photons are emitted backward.
all of them.
Or that they're emitted at smaller radii, and they bump into the shell and bounce backward.
Okay.
But your suggestion is also good, and you should write a separate paper on that, which is just that they're emitted later and they never catch up. And I can tell you that it has, uh, you could make several predictions on the polarization. But we discussed that idea sort of uh, in the context of polarization, but we weren't worried about this shell in front. Um, and I mean, the one question people might raise is that, well, if the shell is carrying the energy, then the emission behind the shell could not have utilized that energy. So why do we have the shell? Well, we have. In real life, we may be stuck with the shell anyway because when you push the star away, you still get the shell that gets pushed out. But the reason that the homework required the shell was so that you have a source of energy. And the question would still be, what's the source of energy? Now, I can tell you that the situation is not as bad as as the simple-minded homework would make it, because if the baryons are being expelled continually, like the photons, over 30 seconds, then you can calculate the energy density. You can calculate the proper density of the outflow, which means instead of being in a thin shell, it's in a shell that's of order R in thickness. It's going as 1 over R squared, but most of the optical depth is over a length scale that's comparable to R. So it's a thick shell, it's not a thin shell. And then the photon that's going outward, since the shell's moving at beta c, the relative velocity is 1 minus beta times c, so the photon only goes through 1 minus beta, a fraction 1 minus beta of the shell. And maybe we should draw a picture here. Okay, so you have a thin shell, and this is a lot like Rahul's idea, in the sense that the thickness of the shell is of order. Oh, come on.
The horizontal is called bar.
What?
The horizontal is called bar. There's a thing. It's upside down.
Yeah, how do I turn it?
Oh, it's there.
Where? Where?
It's there.
Yeah. Where?
This skull bar. This, yeah.
Oh, okay. Yeah, so I have a thick shell, and it's moving outward at beta c, and the photon
VC upside down.
That's not going to help. I have to rotate it. There's a way to rotate it.
Yeah, you have button.
What, this?
Yeah. But then we'll obviously rotate it. No, it's everything is rotated.
What?
No, it's everything is rotated. Look. Look there.
And for me too.
Yes. You should move.
Alright, now at least it's rotated just for you and not for me. Right. Wait a minute. No.
No, you use the
Don't use OK. Just get rid of it.
rotate the entire screen.
I just want to get rid of this thing.
The recording?
I don't want to. No, I don't want to stop recording. I just want to get rid of the goddamn.
The minimize.
This.
Yeah.
Okay.
Use the same button, rotate everything and select one. The same button you use.
This?
No, there's a button to rotate here. Use it 2 times. Okay, one more time. Maybe press wrong button.
No, it's not turning.
No, it's okay.
Okay.
Below.
What?
Just next to Internet Explorer.
What?
Yeah, just below, a little bit below.
Can't hear you.
Move your pointer.
Here.
There.
No. There's something in here. Is there a way to return just this window?
You're gonna maximize everything? Before the
Yeah,
sound?
No.
maximize it.
To turn it around.
Yes, but maximize it. No.
But that's okay. Why would you want to turn it on?
Maximize it.
Yeah. Maybe in a view. In the rotation in a view, without.
But now it's okay. Now here.
Ah.
Now it's okay.
Okay.
Alright, I'm going to destroy here. You have a star, you have a wind, moving at beta C. So the density is tapering off. But the thickness is typically of order R. But the photons which are moving at C only have a relative velocity of 1 minus beta times C. So they only go through 1 minus beta of the total. Now, if you had started from back here at a distance of order R, it would have taken them 1 minus beta to catch up. So actually, as long as the actual optical depth, which is equal to sigma over 4 pi r squared, it really has to be less than 1 over 1 minus beta in order for this to be transparent. And this is of order gamma squared. And so to have 10 to the 51 ergs, the sigma, which is equal to the total mass No, I'm writing this wrong. Let's call this the true optical depth, okay? Instead of tau, tau will leave for proper time. Now this is equal to 4 r squared sigma Thomson, because each proton has an electron that offers sigma Thomson. This is the total number of protons. And the optical depth is just the number of, it's the area that will scatter divided by the total area. And the point is, as long as 1 minus beta times sigma is less than 1, you'll be able to see it. So for a gamma of 100, if you got sigma goes as 1 over r squared, for a gamma of for a radius of 10 to the 13th, you got a sigma of order unity, right?
This capital M is the energy we see here at Earth.
No, it's the total mass in the shell.
But it's not observable when you say to use 251 ergs.
Yeah, but that gave you a certain mass.
Yeah.
It gave you a mass of 10 to the 51 ergs over gamma. This is actually the rest mass.
Yeah.
So M is equal to 10 to the 51 ergs over gamma, sorry, we call this capital gamma, MPC squared.
But how do you know the energy in the shell?
Just a second, M over MP, what?
How do you know energy in the shell?
I'm assuming that the energy in the shell is somehow making the radiation. That's what most people assume. They don't know how exactly, but
if you say that most energy are coming from photons that are emitted back behind the shell, then
just a second, I'm not talking about what I'm saying, I'm talking about what most people say.
Okay.
Most people say that it's a continuous wind and that it has internal shocks, so the amount of energy released in radiation is comparable to the energy in the wind, and then they use this for both. This is the number of protons. Okay, so the point is sigma at when r was equal to 10 to the 13th centimeters was of order unity. That's what you calculated. But that means that sigma of r, say, equals 10 to the 13th over 2 gamma squared centimeters is of order 1 over 1 minus beta. Sorry, this is now the square root, because sigma goes as r to the minus 2, right? So r can actually be a lot less than this. It can be 10 to the 13th over gamma, which is more like 10 to the 11th. And if you divide by the square root, it's a couple of light seconds, which means that they can barely fit in the pulse widths in gamma ray bursts tend to be seconds, much shorter than the whole birth, sometimes even less than a second. But since
That's a square root
since
of 1 over
since
1 minus
since
beta, right?
since the the um, the effect of optical depth. Here I'll use tau for
This
effect of
one.
optical depth. It's proportional to E divided by gamma cubed, because it was E over gamma just to get the brute optical depth, and then I had another 1 over 1 minus beta.
It's not 1 minus beta, not 1 over 1 minus beta, and a square root.
The radius goes down, this optical
But,
depth goes
but
up.
1 over
No,
beta
no,
is equal to like 1
the
minus beta.
radius goes down, the optical depth goes up. This is small denominator. Big number, small denominator. So because of the gamma cube dependence, if I had made it 300 instead of 100, then I could easily fit sub-second subpulsars into a gamma ray burst. And that's how they arrived at the number, that's how we arrived at the number several hundred. I mean, and in particular, Mazaros and Rees needed that number to get, because they believed that they had a lot of matter. And you can also see Levinson and Eichler, 93. This discussed internal shocks, and this discussed internal shocks. But this discussed the photosphere at a few times 10 to the 9th degrees, centimeters. So that's how the world solves the problem. But they don't solve all the problems, because even if you say the photosphere is at 10 to the 13th over gamma, over square root of 2 gamma, it's still much bigger than the radius of the photosphere that you need. Now there's another thing that helps you, which is the gamma ray bursts are very collimated. They're actually, instead of being spheres, they're actually jets a few degrees wide. Does that help you? No, it doesn't help you. It hurts you, because it means that the isotropic, if it were spherical, it would have 10 to the 54 ergs, not 10 to the 51 ergs. And then the amount of matter would go up. So they would just simply have to raise the gamma.
It will go down, right? Because isotropic means larger. If collimated, then you need less energy.
No. But the numbers you got assume 10 to the 51 ergs spherical.
Yeah.
It's still 10 to the 51 ergs collimated, but if you had the same emission in all directions, it would be 10 to the 54 ergs. In other words, it's the same amount of matter, but collimated so that its density is higher, not lower, and the optical depth goes up. So then you need an even larger gamma. Um, so that's where gamma ray bursts are now. That there's still this tension, and Yuri and I, Rahul was here. He watched us argue about it for like 2 hours yesterday. Uh, if you wait until it's optically thin, then you have to ask, how do I manage to get what seems to be a thermal peak all the time, peaking at about the same energy? And some people just wave their hands. Some people say that the photons are made at much smaller radii. And some people aren't aware that there's a problem, and they don't say anything. Okay, so much for the homework. Now let's go to plasma waves and pick up where we left off last time.
Let me load that one.
Lecture 6?
Shown is lecture 5.
Yeah, but we were just on lecture 5.
No, we were at different. Now this is.
This is stuff we did. Oh, he put everything starting from synchrotron emission into lecture 5. Okay.
He has problem with my walk.
What?
He hurt his leg.
Oh.
My knee.
What is this? In the building?
Yeah.
His feet?
Yeah.
Okay, this is where we were last time. First, we did the high frequency limit, where omega cyclotron over omega was a small number. So the frequency of the wave was higher than the frequency even of the electron gyration, the electron gyro frequency. So that this was a small number compared to 1, and it was a small correction affecting phase velocity of left and right-handed circularly polarized modes. Now let's go to the opposite limit, the low frequency limit, where omega is not only is it less than electron cyclotron frequency, it's less than the ion plasma frequency. So these are the polarization vectors basically for left and right circularly polarized modes. But now we make the opposite approximation. We assume omega divided by the ion gyro frequency is small. I guess here I should have said the ion gyro frequency was capital omega. This is the plasma frequency, and I don't think you have to assume that. We'll see, maybe. Anyway, the point is that you can rewrite this as this, and here I just rewrote what omega j is. It's EJB over E squared. Oh, well, this has an m in its denominator, which means here it would be in the numerator, and it would cancel out this m. So the m in omega cyclotron J cancels out the M and the plasma frequency. So you get something that doesn't depend on, the first approximation does not depend on the mass of the particle, which means the electrons and the ions, the first approximation, have the same polarization vector, except that they have a different charge, so their current cancels out. If I sum over J, this first term just gives me 0. But the second term gives me twice omega over omega J because not because of this plus and minus, but just because this term is
You should also say that omega is much smaller than omega I.
well, so far this is just algebra.
Yeah, but only if omega.
This term, regardless of omega I, this term sums to 0 when I sum over J. So it's going to be 0 either way, and here omega over omega I is much greater than omega over omega cyclotron electron, right? Omega cyclotron for ions is much less than omega cyclotron for electrons, because the mass is in the denominator.
You need both of them to be much larger than omega.
We'll see.
No. In order to make this change, you need both of them to be larger than omega.
For electrons and ions. No, but that's what I said. If it's less than omega I, it's certainly less than omega E.
No, I'm not talking about this.
The question.
Both of them needs to be larger than omega.
Well, they are. They are, because if the ions are, then the electrons certainly are.
Yeah, but what? If it's what you're reading, then yeah, because what it's type in there, it's not.
No. I wrote omega is less than omega I, which is less than omega E. So anyway, this plus and minus refers to right and left circularly polarized, and the J refers to the plus and minus charge. Anyway, if I keep track of the pluses and the minuses, I find that the total current is dominated by the ions. And it's of order omega pi squared divided by omega cyclotron I squared. Now physically, why is it dominated by the ions? Because ions and electrons both drift. And we didn't even talk about drift yet, did we? Okay, so now to what? If I have both an electric field and a magnetic field, and I solve, how do I solve for the motion of ions and electrons? Okay, I have a magnetic field, and I also have an electric field.
We go to the reference frame of electron field?
You go to if the electric field, assume the electric field is perpendicular to the magnetic field. Okay? So I go into the frame where V cross B over C is equal to minus E. And then there's no force on an electron at rest, or a proton at rest.
And it's not on the conductivity
No, because the conductivity is defined relative to, depends how you define conductivity. I don't want to get into that now.
the same is when not only in the conductivity.
Well, I can't hear you.
When you say this V equals B is equal to minus E, is not in
The V is the velocity of the frame. V equals the frame velocity. So if I'm in this frame and the electron is at rest in the other frame, then in my frame the electron is moving at V. And let's assume V is non-relativistic. Then E and B are going to remain essentially the same. Or you could say it differently. If E prime is equal to E minus V cross B over C, then E prime is 0. So you know in that frame, the solution to the equation of motion is that the electron just and the proton, they just sit there if they're not moving, and if they're moving, they just gyrate in that frame because the electric field is 0, and we know how to solve the problem when there's no electric field. So the point is we go into the 0 electric field frame. Zero electric field frame. And I'll call this sometimes the 0 zero electric field, ZEF. Now if I transform back into the lab frame, I see an electron that's gyrating perpendicular to both the electric and magnetic field, because V cross B was equal to E, which means that V is perpendicular to E, because E is equal to V cross B, which is perpendicular to both B and V doesn't have to be perpendicular to B, but it means it's a perpendicular component. It defines a 0 electric field frame, and you're free to transform along the magnetic field any way you want. It doesn't create an electric field. So, in fact, I'll make this. Well, I should make these vectors. Okay.
and there's no plus E plus V plus minus. If you want it to be 0.
What?
If you want it to be 0, it's plus.
depends what the sign of V is, right?
But that's also a vector. V plus V over C equals minus E. That's a vector. So
Yeah,
it's E
they're all
plus.
vectors.
Yeah, so it's E plus V times V plus C. Yeah. It's not a minus.
How do you know it's not a minus?
Because E equals minus V cross V over C. You want it to be a zero.
No, I want E prime to be 0.
Yeah. So E equals minus V. So here it's a plus.
Alright, just... Alright. I checked the signs, how do we check the signs here?
I don't understand that. You want the E prime to be zero.
The force, the Lorentz force,
Is zero.
is V cross B over C. I want V cross B over C to equal minus E.
But Lorentz force here is zero because E plus V cross B over C is
Just a
zero.
second. Yossi, just be quiet for a second. The force on the electron, if the okay, if the velocity of the electron, the Lorentz force is the velocity of the electron cross B over C. This has to equal minus E. Now, alright, let me go back to this picture. E is perpendicular to B. I want V cross B to equal minus E, which means V has to be in the downward direction. So the V cross B, I use the right-handed rule, is equal to V cross
No.
B is equal to minus E, right?
V goes to V goes to the other side.
You see, V is going down. This is V. V cross B is going towards me. Down cross right means coming towards me.
V goes down, V cross V goes right. Okay. So you get E goes towards you.
You see, V cross B
Yeah.
is the force. The V cross B is towards me.
Yeah.
The electric field is away from me,
Yeah. Ah, okay.
so
Ah,
they
okay.
cancel.
I thought E goes towards you.
Now, if I'm sitting in this frame, if I'm sitting in this frame where there's an electric field, and I want to move to a frame where there's no force on the electron, then I go to a frame that's moving up so that the electron seems to be going down. So let V be the frame velocity. It's opposite. I think it's opposite the electron velocity, but I'm not even sure at this point.
Okay,
The
so
point is
it's
that
okay.
the point is that in the new frame there's no electric field. That I'm sure. I have to go to the frame where there's no electric field, and you can figure out what that is. But it just happens to be the frame when an electron in the old frame that's at rest is going at I think that this is equal to minus E cross B over B squared C. I think the minus sign is in there because E cross B is down. That's the direction I want the electron at rest to be going in, which means I have to be going up so that the electron will appear to be going down. Okay. Now this, you were witnesses, I didn't do anything, and it disappeared. Okay. So now where were we in regard to the plasma waves? Here, I I wrote it down here, but I think there's a sign error here. Where were we? Here, we were right here. And the point is that if I calculate all this stuff, I don't know what this beta is. I have no idea.
No, it was supposed to be P. Instead of beta P.
Okay, so this is where I use the fact that omega I. Wait a minute.
It's smaller than omega.
Yeah, this is now. For the first time I will invoke the fact that omega pi is greater than omega cyclotron I. And that means I can neglect this one, roughly. So in that limit, epsilon is c squared over the alpha angular velocity squared, where the alpha angular velocity is defined to be, this should be an n, not an h. And this is just the just a second. And this should be an E, not a C.
No, it's a C. Remember, it's a C.
No, it's an E.
Why? But the meaning is B over 4 pi volts.
Oh, wait a minute. You're right. It is a C. It is a C because it came from this thing here, and the E squared canceled out. You're right. You'll see it's a C. And the phase velocity is VA. If epsilon is because the phase velocity is the square is 1 over the square root of epsilon times c. So it's just v sub a. And v sub a is defined to be, this should be a small m. It's equal to the square root of b squared over 4 pi N and P. And sometimes we write this over 4 pi rho. Okay. Now, to lowest order, the electron and ion current canceled. Why? Because they were both drifting. And they were both drifting in the same direction because the zero electric field frame doesn't care about the charge. It's the zero electric field for all charges. But why is the current not exactly zero? And the answer is because it takes about half a gyro period to start drifting. In other words, if in the zero electric field frame, the concept of drift only has meaning on the time scale of a gyro period because it's the guiding center that's drifting. If the ion has a finite velocity in the original frame, then the magnetic field is going to cause it to gyrate, which means it's accelerating. And then even in the transformed frame, it's still gyrating. It's just that it's gyrating around a fixed point.
Right.
Because there's no electric field to make it go anywhere. And therefore, until you can tell that it's drifting, it takes half a gyro period. Until then, if it was at rest, and even if it was at rest at the lab frame, when you change frames of reference, am I saying this right? I don't know if it takes half a gyro period. It's just that the correction, the reason it doesn't, when the assumption was in the zero electric field frame, there's no net force, no time average force on the particle. But if you have an electric field, a wave, the E cross B direction is constantly changing, so there's going to be an inertial force which will be proportional to the mass. And the difference between the ions and the electrons is really, of that force, is really proportional to the ion mass. In other words, to zeroth order, we saw that there was no dependence on the mass. Out here, there's no mass, and this one is not. So we could have taken the mass equal to 0. And that's why to lowest order, the electrons and ions give the same contribution, because it just doesn't depend on the mass.
First order.
To lowest order. The next term does depend on the mass, and because the ions have a larger mass, it's harder to get them to drift, along with the electrons. Now the electron, to say there's a net current just means that the relative velocity, the electrons and ions, is different. It doesn't make sense which one of them to blame. But in the lab frame, I think that the ions are the ones that are generally moving further from the drift velocity than the electrons, because they have a larger inertial correction. So, okay. Now, just to review how we figure out what a wave does, we calculate the polarization tensor and we compute its eigenvalues. For Alfvén waves, it didn't really matter whether it was plus or minus. It just ended up to be the same for both. For high frequency waves, there was a slight difference between circularly polarized right or left. So we had to know that the eigenvectors were circular polarization and not linear polarization. So that's why once we find the polarization tensor, we have to find the eigenvalues of that tensor, so we know what the modes are. And various terms in chi, the polarization just represent the different contributions to the current, as seen in the lab frame, from different ions, from charged particle species. Now, if you think of the field lines as being in the zero electric field frame, then if the zero electric field frame is moving with respect to you, you can think of the field lines as blowing past you. That's an intuitive way to think about it. And I think they drift at minus E cross B over C. Somebody, I don't have my Jackson here, but I'm pretty sure it's minus E cross B over C.
C cross B over C. It's plus sign.
It's a plus sign?
Mm-hmm.
Just a second. I can do it. I just did it before. The frame in which the electric field vanishes is the frame in which an electron wait, I'm sorry. It's the frame at which the electron. Let's go back to this picture. Alright, the electron is moving in the y direction and B is in the x direction. An electron moving down. You're right. An electron moving down would have zero force. So the frame in which an electron at rest would see zero force is moving down, not up. And therefore this is plus E. No. V cross B is equal to minus E, and therefore the
electron is equals B.
the frame
So
velocity.
it's minus equals B.
What?
The frame velocity is minus E.
No, Rahul just convinced me that it's the frame moves with the electron. Yeah, I said it wrong last time because an electron at rest has to feel zero force.
Yeah.
In the drifting frame. Yeah, so it has to move with the electron. Okay. And E cross B is, so it's plus. Okay. Plus. And then maybe this is plus too, because E cross B cross B. What's E cross B cross B? It's minus E, right? E cross B is minus E, so this is a plus. Is that right?
E cross B cross B.
Line velocity is in the same direction.
is it's minus E, right?
Mm, yes.
Yeah. Okay.
Uh, the flying velocity is in the same direction with the electron.
Well, electron in the field 0 force. Yeah.
So can you go up a little? What I see from here is that here, if it's in the same direction, so E plus V. Can you just change this to V? If VE and V is equal, so it needs to be minus.
Just a second. Wait a minute. Wait a minute. You guys are getting me all confused here. V cross B, the electron is minus E. V cross B is minus E. And therefore,
That's also minus if it's in the
no,
same direction.
V cross, this is minus V cross B cross B
It is correct.
if it's minus.
If V and VE is in the same direction, so it
Yes.
will be plus.
Then because you're writing two frame and you're using the same
I'm hot. I'm too hot.
Uh,
Just a
no.
second.
Oh yeah.
Because VE is
Just
also
a second.
E plus
We
P.
agreed that the electron is moving down,
Yeah.
and we agree that down is E cross B. So it's plus.
Yeah, this is correct. Yeah. And now this is correct also. Just
Yeah.
say it at the
Okay.
beginning
Yeah.
and it's plus.
Okay. All right. So listen, we just did the high frequency and low frequency. Where high frequencies, the inertia of the lightest particles is important. In the low frequency,
And you should also delete the minus from there.
yeah, okay. Anyway, if you view the field lines as moving with the drift, uh, as moving along with the drift, then you could think of the field lines as blowing past, as also drifting. Now, as the particles are drifting, but if you think of the field lines as also drifting, then you could think of the field lines as being, you could think of the particles being stuck on the field lines.
Okay.
And that's why in the alpha and in the low frequency limit you have magnetohydrodynamics, which means the particles are always stuck on field lines. You can prove it magnetohydrodynamically, but here we prove it plasma physically, that the if you think of the field as moving, if you think of the field lines as moving in the zero electric field frame, then the particles are always stuck on the same field lines, which means the field lines are frozen into the plasma.
Yeah.
That's the opposite way of seeing frozen in field. So And the opposite limit, where omega is larger than all the gyro frequencies, then the inertia of the lightest particles is somewhat important in making small changes, opposite signs, the right and left circular polarization. But now there's an intermediate limit, which is where m sub I is irrelevant because it's too big, because the frequency is changing directions faster than the ions can respond. So the frequency is I think also has to be bigger than the ion plasma frequency also. Okay. In that case, why is this not moving? Okay, it's just stuck there.
The spin.
Because what?
Because of
The
pen.
the pointer is
Okay. Alright, so now if omega is much less than omega cyclotron E, then this term in the dielectric tensor is approximately this. Again, plus minus a right and left circular polarization. And if I put an omega I here, I would also put one here. But then I would have omega squared over omega. I would have omega pi squared. No, the term I'm neglecting is of order omega pi squared over omega squared. Right? And that's we're assuming to be very small. But this term, the electrons, is not small because regardless of whether omega cyclotron is greater and less than omega plasma for the electrons, this term here is omega is less than both of them, so this fraction is generally going to be large, unless this is so much, unless the magnetic field is so super strong that this compensates for the smallness of omega. But in that case, you'll get something that moves approximately at the speed of light. You'll get an electromagnetic wave that moves at the speed of light, and it just doesn't matter what you call it. But when it's called Whistler modes, it's because this fraction is much greater than 1, and therefore epsilon is much greater than 1. And therefore this phase velocity is much less than the speed of light.
Why Whistler?
Because
It's not the name Whistler.
no. Because when they were first detected in the Earth's ionosphere, what is the frequency? The frequency is this.
Okay.
What the hell's going on here? And if you just solve this equation, you get that omega is proportional to k squared times this number, that it's a frequency times c over square over omega p squared, which dimensionally cancels out this k squared. But notice that the higher k gives you a higher omega. But also notice that the phase velocity phase velocity is equal to omega over k, which is equal to k times and we'll put this over alright, we'll keep it here. We'll keep the c squared here. But unlike Alfvén waves, where the phase velocity was just the Alfvén velocity, it didn't depend on k. Here, the phase velocity increases with k. Now, when they first detected them, where were Whistlers made? It turns out they're made in the Earth's ionosphere. And when they had radar detection, the radar, I think in World War II, the radar was picking up Whistler waves because they're antennas, they detect electric. And for some reason, the amplifiers were the frequency of the waves was comparable to the must have been comparable to the resonant frequency in some equipment. I mean, let's work out what this is. In the Earth's ionosphere, k can be very small. In the Earth's ionosphere, you can have very long wavelength waves, so k can be.
Take this piano.
I still don't understand why the pen sitting here makes a difference.
Because it can feel it. This.
No, but these are supposed to be independent. Here, look. I have this tip and I have.
Right.
Oh, it's only one or the other?
Yeah, they're different.
Oh.
They
Okay.
come close, they interfere with each other.
Okay. So I don't know what this is, but but the point is it's low frequency. It's like thousands of kilohertz, which the ear can hear, and which may have resonated with some of the electrical equipment. But the point is the higher frequency radiation, which has the higher K, arrives first. Notice you have a lightning pulse in the Earth's atmosphere that generates Whistler, or in the ionosphere, maybe the stratus. I don't know. I actually don't know what triggers them. It might be lightning, but I'm not sure. You can Fourier transform the wave pulse into different Fourier components, but then the higher frequency ones arrive first, and the lower frequency arrive later. So you start off like this, and a little while later you get. So what they were hearing was things that went meow, or they sort of made a whistling sound that went down, like whistling a pretty girl, like. So that's how they got to be called Whistlers. Um, And we once did some work on Whistler's inhibiting heat flux in astrophysics, and heat flux instability makes Whistlers. So when I gave the talk, I said, heat flux is the mother of all Whistlers. And I showed a picture of the woman in the painting with a thought balloon over her saying, how to make Whistlers. Okay, are there any other interesting regimes? And the answer is yes. Suppose k is small, but suppose omega is very close to omega p. So k squared c squared over omega p squared is very small, and it's equal, but it's the dispersion relation says that this has to equal this, right? Wait a minute, what's the dispersion relation? For an electromagnetic wave, what's the dispersion relation? It says that k squared c squared equals omega squared times 1 minus p squared. Is that how it goes? I can scroll up, but
Omega over omega 3.
what?
It should be omega over omega p, no?
No, the deviation from 1 is proportional to omega p squared. F, just a second. Just a second. Let me just go back and check.
And there it say it's 4 o'clock.
Okay. Alright, that's a great suggestion. Then I'll figure it out. Yeah, yeah, alright, so tomorrow I'll get this straightened out. But the point is, there's one more place where if omega is very close to omega p, then 1 minus this is a very small number. This is the phase velocity, and this is also small. And maybe this is without the p. Maybe there's a misprint here. I'll work it out. Okay. Alright.